Let us talk about transition curves and what options there are to define these transition curves within ABES geoDes. A typical transition curve provides the transition between a straight line and an arc element along a road or railway alignment. In some rare cases, a transition curve may also provide a transition between two arcs of different radii. Here is a small example in ABES geoDes that I will be using for this video. This example is available from our website. We have an axis input dialog up here, and I've opened the plan view definition. The plan view for the axis shown in the representation in the diagram at the bottom here, the IP polygon, is defined in these first three columns: a name, easting and northing values for each point along the IP polygon. And each corner of this polygon is rounded according to the definitions shown here on the right side of this table. Let us quickly zoom in on one of these rounded corners. Let's take point 3 of the IP polygon, and let's look at the rounding. So we have a straight coming up from the second point, and then we have the first transition curve starting at this point here and ending at this point marked with a cross here. After this cross, we have a arc section, a circular section, up until here, where this next cross marks the beginning of the transition curve leading out of the rounding and into the next straight. So each rounding typically consists of a transition curve in, an arc section, and a transition curve out of the rounding. Here is the input for the third polygon point that we've just looked at, PV3 in here. We have easting and northing data, and then we have a type, and we will discuss the options for the transition curve type in just a little while, and a number here defining the incoming transition curve. Then we have the radius for the circular section, and then again we have a type and a number to define the geometry of the outgoing transition curve. Probably the most commonly used transition curve in plan view road alignment design is the spiral curve or clothoid curve. And the first two options up here relate to that spiral curve. The formula is showing in the left corner of our screen right now. In many cases, the road designer will provide the length of the transition curve, and that is input type len that I've used here in this example as a default, and 50 is the input. So in this line here, I'm asking for a transition curve of the type spiral curve with a length of 50 meter leading into that first radius, and then again a spiral curve with a length of 50 meter leading out of the rounding altogether. Alternatively, and that's a fairly common occurrence with European based designers, the clothoid is defined by this parameter A, which is the rate of curvature change along the chainage of the axis. And if we use this definition, that parameter A needs to be given here in that column P1 as the associated input. And if we look at this rounding where this line relates to, this changes the geometry of the rounding, obviously, because we are now using a different type of information for the input. I'm switching back to len for now. The most common approximation to the spiral curve is the cubic parabola. It's a bit of a relic from pre-CAD system times, but it's still popping up every now and again. And if it does, it can be defined in here using the parabola A and the parabola length input options. So parabola length requires the length of the transition curve as the input, and parabola A will require the rate of curvature change as an input. And when we choose that, the computer, or ABES geoDes, will use a cubic parabola instead of the spiral curve for the transition curve. Sine half-wave formulations are sometimes used for transition curves in plan view for railway lines. Here is a mathematical formulation for this particular transition curve. It's a tricky one because the rate of change of the curvature is no longer linear, and because of that trickiness, call it that, some software packages use approximations when using this or when calculating this transition curve. ABES geoDes has the exact solution for this sine half-wave transition curve implemented here, and if we use that, we can already see how the transition curve shifts to a slightly different location and different geometry from the initial clothoid that we have recorded with our orange dots here. And since we are trying to replicate the alignment as provided by our consultant, in some cases a problem has arisen when consultants use the approximation provided by some CAD packages instead of the exact solution, and the results differ therefore. So in geoDes we cater for this instance, and we have also implemented the approximation that's commonly used in other packages for the sine half wavelength. So going away from the exact solution to the approximation, again it shifts the curve a little bit, and if the consultant uses an approximation, it's best practice to use the approximation within ABES geoDes as well, so we can match the data accordingly. This brings us to the final two entries in this list, the CCA and the CCLen entries. CC stands for compound curve, which is the rare instance where one radius leads directly into another radius without a straight in between. So the clothoid provides the transition not between a straight and a radius, but between one radius and another. To explain the compound curves, I've prepared a separate example up here. This is a small alignment, a small axis, again the plan view input tab here, where the compound curve function is used. Again, we are using the length input option as opposed to the A option. Remember, that is the clothoid parameter. We're using the length. So In this example, we are using a 50-meter transition curve to go into a 580-meter radius, and then we are using a compound clothoid to take us directly from the 580-meter radius to the 400-meter radius. And at the end of this, we're using another 50-meter transition curve to go back to the straight line. Since we are only using one clothoid to go directly from 580 to 400, the input up here becomes obsolete. As a matter of fact, in ABES geoDes, we use the CC-len or CCA parameter with the smaller radius, and simply put the clothoid parameter or the transition curve parameter for the larger radius to 0. If we draw that up, if we draw that up, looks like this. We're starting with a short straight and go straight into that first 50-meter transition curve, a clothoid, a simple clothoid, which takes us to this 580-meter radius. And that 500-meter radius ends here. We're going straight into another clothoid and into the 400-meter radius here. And at the end of the 400-meter radius, we have a 50-meter clothoid to take us back to the next straight. Let's look at the data with the numbers in front of us. If we go down to the elements, we have a straight line going into a 50-meter transition curve, a clothoid, going into that first arc with a 580-meter radius. We have a nominal 1 millimeter straight here, which basically gets rid of rounding errors. So let's ignore that 1 millimeter straight line, because now we are going into a clothoid that takes us from the 580 meters to the 400-meter radius. We then have an arc again and another clothoid of 50-meter length out of that second 400-meter arc. This is the compound curve as it is implemented in geoDes. The same axis, only upside down, starting from here and going all the way to here, is contained in this second compound curve reverse example. And as you can see, in this case, again, we are using the CC-len parameter with the smaller radius, which comes first when you go the other way, and put this transition curve to 0 for the larger radius. Same curve, except in the reverse direction. The CC-len parameter goes with the smaller radius.